So we're now here. Our tensor is right here. So the moment I run this, we're now going to enter into this conf class right here. So I'm just going to step over this since we have already covered conf classes. And now the moment I run this will be right here. So you can see conf class will change to now this upsample. And as its name indicates, the upsample module upsamples the image based on the upsample algorithm that is selected. So in this case, the default is nearest, and is also the one that we're going to be using here for this upsample with a scale factor of 2. So let's go here to other modules and open Upsample. And you can see that this is the same that we have here, where we're filling in 1 by 512 by 20 by 20, and then we're upsampling it by a scale factor of 2. Now we just came out of the SPPF module, so we already have xout9 stored locally. You can see xout9. But if you just started this video, you'll have to run the texture model, run in cells, and then you'll have to uncomment these ones so that you can actually save those variables. In our case, we already have those, so we can run these. Now, there's a conf class prior to this upsample. And if we output the first channel and then the first 4x4 values of that tensor, of that xout10, we obtain this. And then if we do the same, but for the tensor that has been processed in the upsample module, and we output not the first 4x4, but the first 8x8, you can see that given that we're using the nearest neighbor algorithm for upsampling, this -0.01, this 1 by 1, now is at 2 by 2 due to this scale factor of 2. And then this 0.26 now has these two values on the columns and on the rows. And similarly for this one, these two values, and same for the rows. So this is just to show all that it has done here, which is gotten all the values and then scale them by a factor of 2. So your output has twice the size, basically, for every channel. And that's what the upsample module does. So here we can just perform that. And now we are in the concatenation module right here that takes two inputs, the input from the previous layer as well as the input from this C3 module. So let's open that one. So if I run this, we can see that that's the module, and we can see that that F has this list of -1 and 6, and that is because the input is coming from both the previous layer as well as stage 6. So for the first time, now that we're in the neck of the architecture, our input is going to be different from just -1. It is the first time that we have an input that is coming from two different places. So basically, we're going to do this step in our Colab environment, step by step, to unpack it a little bit. And what I'm going to do is this, move this here. So here, I'm just redefining our M12, our stage 12 or module 12 to M, so that we have the same values as here. And then the same with xout11, just the immediate layer, X, which is the same one as here. I'm just calling it X. So again, if I call M.F, this is what we obtain, -1 and 6, as we already knew. And basically what this is calculating is saying if M.F is different from -1, well, it's a list, M.F. If it's different, then step into this, and then give me Y. So Y is right here. And right now we have a value of 12 in terms of length, and this is Y here as well, where we've saved the tensors of the backbone layers that we knew we were going to need later. So we save 4, 6, and 10. Layer 4, you can see 0, 1, 2, 3, and 4, that output, 5 and 6, 7, 8, 9, and 10. That will be here. We'll use that one later, as well as these ones. But here, at this stage, stage 12, these are the tensors that have been saved. So here, given that M.F is not an integer, it's a list, this will not apply. Instead, if j is equal to -1, in the first case, which it is, then we'll get the input, we'll get x. We'll get x as one of the inputs, and then if not, for the next one, if it's not equal to 1, then we'll get y6. Y6, we'll get that tensor. And that will be in a list that will be stored in this variable. In this case is x. We're calling it x_in for the input to this module 12. So if I run that, and then this is the same, I could run this as well, but basically this is the same as having a list of the previous output as well as the output of stage 6. This is what this has performed. So if I run this, you can see that we'll step into this, and then x is this value. So we are reading this first index, j-1 and j6. And the moment I run this, x will be a list of those two tensors. So you can see we have those two tensors, which corresponds to the previous layer as well as stage 6. You can see this -0.27 is this -0.27. So here we've calculated with this function, and then here we're just literally create a list. Now these two should be equivalent, and if we run this, and then this other one, if we compare here the output from both this list with this function as well as us manually putting it, well, we're going to get an error because we're comparing list of tensors. You can see the torch that all close, this xin right here, and this xin underscore. We cannot compare list of tensors, but what we can do instead is compare each of those tensors. So index 0 for those tensors, as well as index 1 for those tensors. And we can confirm that what we obtained here is the same that manually. And then if we output the shapes, we can see that the concatenation happens on this dimension. So M, you can see D for dimension, D of 1, which corresponds to this self.d right here, D of 1. So it concatenates on that dimension, on the channel dimension, so that these two tensors, this 512 right here and this 512 right here, they get concatenated for an output shape of 1 by 1024 by 40 by 40. So we're going to run that, and then what we're going to do afterwards is each of these following operations, this C3, conf class, upsample, concat, another C3, this conf class, concatenation, another C3, this conf class, concatenation, and C3. We're going to perform those very quickly. We'll step over those since we have already covered each of those modules in more detail. And we're going to go all the way to this final class called detect. So let's go ahead and do that and just step over this current module and then the next modules until we get to the detect class. So once we run this, we'll get out of the concatenation and we'll be right here, getting into the C3 module, as you can see here. And now we're going to step into this conf class. We perform the upsample, and now we're here, another concatenation. And now we're going to step into this C3 module. Now we're going to jump right here to this conf class. And now we're going to jump to another concatenation. Now we're going to jump into this C3 module. By the way, all the C3 modules within the neck of this architecture do not have the skip connection. So let me show you. You can see M, sequential, modules, and then each of these bottlenecks, the add is equal to false. And that is because in the bottlenecks, you see the shortcut is initialized as true, meaning that it has a skip connection, but here we're overriding it because that add right here is equal to false. So that shortcut will be false, and therefore, given that this is false, we'll only perform convolution 1 and then convolution 2, and will not add this skip connection. as we did previously when we performed the C3 of the backbone architecture. So let's step over that. And now we're about to jump into this conf class. And now this concatenation. And then this final C3. And now we've concluded these stages all the way up to this class, which we're going to cover in the next section.